But once we are done, maybe with this week and next week, is when now we can start writing Solidity code that will start being interactive, and also as mentors will be taking turns. So yeah, hopefully that will be of great help. So I'll start presenting.
Hi, Sharon.
Hi.
Your network is fluctuating, so sometimes you go off and we don't hear you.
Okay. Yes, can't speak.
Okay, so good evening, everybody. So thank you for joining the class early. So Sharon is actually from another region. So you guys will need to pardon her network. Probably she'll be having network issues. She'll be having technical issues. So anytime she jumped out of call, you get lost when she's talking. Just try and as much as possible to be patient and just notify me. You can just call my attention on the Slack, or you can call the track manager's attention also. So I think the track manager for this track is Olubukola, and she's on call right now. So you can just message her and just let her know so she can, solve the issue. So that's all for my hand.
Okay, thank you.
Okay, so Sharon, you can start the class now.
Okay. Just a moment. Okay, I hope you can see my screen. So yesterday.
Yes, I can.
Okay, thank you. So for yesterday's class, we started by covering wallets and just an introduction to wallets, what they do. Then after that, we covered the types of wallets, like the deterministic wallet and the non-deterministic wallet. Just still understanding in much details what the non-deterministic wallet does, and also what the deterministic wallet does. And we saw one type of deterministic wallet in detail, which is the HD wallet. And we also saw the advantages of the HD wallet as compared to other deterministic wallets. Apart from, let's say, the type of wallets, we also saw the Bitcoin standards, the Bitcoin improvement standards that are used to on the seed phrases and the mnemonic phrases that are used for Ethereum and other crypto wallets. So that's majorly what we saw before we started on transactions. Okay. So I'm not sure from yesterday's class, does anyone have a question before we start on transactions?
Oh, okay, I have a question.
Okay.
Under the deterministic wallet, is it only HD wallets we have? Because during our preface, they asked the question and they were mentioning cold wallets and I think hot wallet was there. And I didn't know how they came about those types of wallets. So I don't know if it's under deterministic kind of wallets.
Okay, when we were talking yesterday about the deterministic wallets, we only like HD wallet is not only the type of the deterministic wallets, but HD wallets, let's say, is a main example of the deterministic wallet. That's why it was mentioned. But there are also the different types of wallets that are deterministic, like those that are software based, like the one MetaMask, and then the others that are, let's say, the one like now the hard wallet and the cold storage that you are talking about, which are still under the deterministic wallets. I'm not sure if that's okay.
Yes, it's okay.
Okay. Is there any other question? Okay, so yesterday we finished the class by just starting on transactions, and I'll just maybe go through the transactions as we start. So transactions are signed messages that originate from externally owned accounts that now these transactions are transmitted on the Ethereum network and also recorded on the Ethereum blockchain. So when I was talking about the transactions, say maybe the main things that we look much into is the idea that these transactions have to be signed and they originate from those externally owned accounts. So externally owned accounts are like those accounts on MetaMask. And then once, let's say, a transaction, like someone wants to initiate a transaction, if you have something, you can just speak up. Okay, let me try presenting. Just a moment. I'm not sure if here is much better.
Yes, thank you.
Okay. Okay, so I was talking about the transactions, and I was saying that an externally owned account is like your account on MetaMask. And let's say you want to send someone some Ether, or just want to maybe, let's say, buy an NFT. So to do that, you'll have to confirm on MetaMask. And that idea of confirming is now this signing or verifying the transaction. And then once you have confirmed it or verified the transaction, is when now this transaction will be transmitted through the Ethereum network. Because let's say you are sending Ether or some tokens. And then once let's say the transaction is successful, it will now be recorded on the Ethereum blockchain. So just let's say if you want to maybe define a transaction, you try to talk about it being signed, and then the idea of an externally owned account, and also the Ethereum network, and also the Ethereum blockchain. So just going forward, okay, another way to look at transactions is that they are the only things that trigger the state or cause a contract to execute in the EVM. So for let's say now our contracts is the smart contracts. So for the smart contracts to be executed or to change the state of the EVM, the transactions have to take place, or transactions have to trigger that in order for the smart contracts to influence the state of the EVM. And then Ethereum is a singleton state machine, and transactions are what makes the state machine to tick, changing its state. Normally, let's say when we are talking about the EVM, we talk about it being this state machine that runs now on the Ethereum network, and it's the transactions that make the state of this state machine of the Ethereum to now, for its state to change, transactions have to occur. Then contracts can't run on their own. Transactions have to make it possible for the contracts to run. And then Ethereum doesn't run autonomously. Everything starts with the transaction. So for a case of, let's say, the smart contracts have the contracts accounts. But again, an externally owned account has to, let's say, initiate a transaction, or let's say when you're trying to interact or execute, let's say, one function of the smart contract, you'll have to connect your externally owned account, for example, using the MetaMask wallet. And then that's how a transaction will occur. And also, let's say one contract can also interact with another smart contract. So, we had stopped here on the structure of transactions, and we had mentioned about the nonce, the gas price, the gas limits, the recipient value, and that's the V, R, and S. So I want maybe read this, like I want to try to go through this specific slide because each of them is explained in detail in the next slide. So we can just go through them one by one. Okay, so just starting with transaction nonce. So a nonce is an attribute of the originating address. That is, it only has meaning in the context of the sending address. So this nonce is an attribute of sender's address. Now the person who initiated this transaction. So, however, the nonce is not stored explicitly as part of an account state on the blockchain. Instead, it is calculated dynamically by counting the number of confirmed transactions that have originated from an address. So you can find at times they define a nonce as the number of transactions that have taken place in a given address. So I think here they are saying that the nonce is not stored as part of the account state on the blockchain. Like, okay, let's say I have my own account, the one that is externally owned. Of course, it has maybe a number of transactions that I've undertaken on that given address. So they're saying that the number of transactions that have taken place in that account are not recorded on my account state on now the Ethereum blockchain, because assuming this is an account, of course, on MetaMask, so it will be on the Ethereum blockchain. So that number of transactions that have occurred will not be recorded on this account state. So they're saying that the nonce is calculated dynamically. Okay, so they're explaining how this number of transactions that have been confirmed that originated from this given address. So they're saying it's just calculated dynamically, and that's how we have the nonce. So maybe on nonce, you just take note of understanding what's the meaning of nonce. And at times you'll find that there could be a different meaning of the nonce. Let's say for a case, at times they say that whatever the miner is paid is a nonce. And for this case also, the nonce is now the number of transactions. Okay, the number of confirmed transactions that have occurred in a given address. So just know the context of what, let's say, this nonce is trying to mean. So let's say for this case, it's a case of a transaction. The next one is the transaction gas, and gas is the fuel of Ethereum, and gas is not Ether. It's a separate virtual currency with its own exchange rate against Ether. So Ethereum uses gas to control the amount of resources that a transaction can use, since it will be processed on thousands of computers around the world. So mostly you'll see they are saying, let's say, gas price or gas fee. So when they say gas price or gas fee, they're saying that fee or price, meaning that this, maybe the amount of gas has been converted into a currency. That's why here they're saying that gas is not Ether. It's just a virtual currency, which, so at times, let's say we have our local currencies and they're always put or compared against the US dollar. So let's say now the amount of this gas is now, let's say they can say they are converting this, let's say the gas, the unit of this gas to maybe whey or ether. So it's not directly ether, but the value of this gas has to be put in that exchange rate, so that we have maybe now when they say the gas price, it can now be in terms of whey or ether, or just the unit of gas. And the reason why we have the gas is to control the amount of resources that a transaction uses. So when a transaction, let's even assume, let's say a bank or money transfer, mostly there is that fee that one has to pay for it to occur. So just in as much as we are moving from maybe the ordinary traditional currencies or traditional maybe banking to now the decentralized finance, it's not like we are running away from those little fee that one has to pay. So still, even when people are talking about maybe the blockchain, Bitcoin or Ethereum, they'll still talk about the environmental impact and just taking this idea of gas. Also, it has to be controlled. Let's see, now each transaction that will be happening, there'll be a gas. Now the gas fee, or yeah, I think it's the gas fee associated with this transaction, so that when a user is making this transactions, they know that they might incur a given gas fee, or yeah, they might incur some gas, so they'll have to pay for some gas fee. So I think that for these transactions, they'll be processed on thousands of computers around the world, and these computers are now the nodes. So the open-ended or Turing complete computation model requires okay, I'm sorry for that. So the open-ended or Turing complete computation model requires some form of metering in order to avoid denial of service attack in inadvertently resource differing transactions. So this term, the Turing complete, I believe by now you know that it's possible to write the smart contracts on Ethereum. So the reason why it's possible to maybe write smart contracts on Ethereum is because it's Turing complete. But for Bitcoin, it's not Turing complete. And here they're trying to explain maybe the relation of transactions to the idea that now Ethereum is Turing complete. So now the way here they're saying that the Turing complete computational model requires that form of metering. So now this checking the gas to avoid denial of service attack or inadvertently resource differing transactions. So this could be measures or why we have these gases. So like for every transaction that happens, the gas that is incurred for that transaction has to be measured. Now that metering is now measuring the gases that have been incurred for a given transaction. And one of the reasons is to avoid the denial of service attack, which could be maybe an attack on, let's say, a given smart contract or decentralized application that is on the Ethereum blockchain, or that resource differing transactions, or transactions maybe that take a lot of gas, which could be abnormal. And I remember thinking the preface, maybe you are asked about why they pay the gas fees. And I think most of the answers that I saw was on preventing those attackers. Just people were coming to the network trying to, they're not here to really do something that they are expected to do. Maybe they're here to try and perform some malicious attacks. And also it's a way of just controlling the resources that given transactions gets to consume. So gas is separate from ether in order to protect the system from volatility that might arise along rapid changes in the value of ether. Okay, as we know, the prices of cryptocurrencies like ether keeps changing. So this is what they mean by the volatility. So they made it that the gas is separate from ether, so that whenever the gas, let's say, has been measured, that this transaction took a given amount of gas, so that gas can be, let's say, converted to its equivalent in form of ether or whey. So gas is separate from ether. And the other reason why gas is separate from ether, it's a way to manage the important and sensitive ratios between cost of various resources that gas pays for. So like now this gas, when this gas is, let's say, measured or so, it's so this gas, whenever this, or the reason why we have the gas for the transactions, it's a way of managing, let's say, stuff that make up the Ethereum blockchain or how these transactions are undertaken. And just among the things that, let's say, the gas will pay for are like the computation process, maybe how the miners gets to verify the transactions, and then the memory, let's say the memory capacity that maybe that was used maybe when running that transaction, or which that given transaction occupied on the blockchain, and also storage. So the next thing, okay, the gas field, okay, I think there is the gas, and then now there is the gas price. So the gas price field in a transaction allows the transaction originator, who is now the sender, to set the price they are willing to pay in exchange for gas. So, you know, when, let's say, when a user, because this sender is just a user, so when a user is told maybe to set gas in those units that gas is in, it might not be favorable for them. But when, let's say, the value of gas is able to be converted into its value in ether, which is now the gas price, it's convenient for the user to maybe set the gas limit, the amount of gas they want to spend on this transaction. Like they don't want to spend beyond this. So when a user is given that option of maybe setting the gas limit, so when this option is in ether, like the gas price is in ether, you're able to easily determine that amount that you want to set for the gas limit. The price is measured in whey per gas unit. So just as we said, there is the gas, and then now the value, I think there is an exchange rate for determining like whey is the smaller unit of ether. So there is that calculation of converting the gas price, or I think it's gas price equals to now whey times the units of gas that was spent. There is that formula for calculating it. The next part of the transaction fields is the transaction recipient. And you want to say something? Okay, sorry for that. So you are seeing the transaction recipients, and these are still the fields of transactions, and these are the things that appear when a transaction has been, let's say, has occurred. These are the fields that the user will be able to see, and part of them is the transaction recipient. And this is now the person. If let's say, and I'm the sender, and I'm trying to send someone some ether, so the other person is now the recipient, and most likely I'll be sending to the address. So this field of the transaction recipient will have the address of the other person, now the receiver. So this transaction recipient contains a 20 bits Ethereum address, and the address can be externally owned or a contract address. So it's possible for, let's say, an externally owned address to maybe make a transaction to a contract address, and also a contract address can also make a transaction to, another contract address. So for that field, it will be an Ethereum address, and that address could be, let's say, someone's address, which is an externally owned address, or an address of a smart contract, which is now the contract address. So the Ethereum does no further validation of this field. So when you're, let's say, you want to send someone, you have to be sure when you're, let's say, entering their address. Any 20-bit value is considered valid. So as long as you have entered a valid address, a valid Ethereum address, that field will be considered valid. Okay, if the 20-bit value corresponds to an address without a corresponding private key or corresponding contract, the transaction is still valid. So let's assume you're sending to, okay, let's say an externally owned address that doesn't have a private key. It means that, let's say you entered, let's assume you're sending it to someone, and one thing could be you're sending to an address that doesn't exist. So maybe that an address that doesn't exist might not have its own private key, or because even if an address, let's say someone has an address and they have lost their private key, they have lost, let's say, access to that account will still have the private key. It's only that person cannot access it. So they're saying that if, and for a case of the contract. If, let's say, this contract, okay, you're sending to a contract address that doesn't have a corresponding contract. So maybe that smart contract doesn't exist, or so it will still be considered valid as long as it's a 20-byte address. So Ethereum has no way of knowing whether an address was derived from a public key. And so obviously, if there is a public key, it has its own private key. Remember the key pairs. So Ethereum doesn't have a way of knowing if this address was derived from the public key in existence. So just a warning, the Ethereum protocol does not validate recipient address in transactions. So you can send to an address that has no corresponding private key or contract, thereby banning the Ether, rendering it forever unspent. So validation should be done at user interface level. So this is just a warning that, let's say you send to an invalid address, that field will be considered valid, and obviously the transaction will be successful. And if you're sending someone Ether, the Ether will be deducted from your address, and it will be considered banning. Banning is like, it was not spent, it was not sent to someone, so it has just gone. And even banning happens for NFTs. Let's say if maybe there are excess NFTs, the creators might decide to ban a given number. It's like dispersing. So now for you, if you're trying to send Ether, just make sure that you validate. Try to counter check it before confirming the transaction that you're sending to the right person. So this is just like the normal thing, the way we normally try to send someone money or to a given account, you always have to counter check. So for a case of making transactions on Ethereum blockchain, try to validate the recipient's address. So when they're seeing the user interface level, it could just be on a wallet now like MetaMask, or if the wallet was on an exchange, you still try to validate it before making that transaction. The next field is the transaction data, or the payload. So the payload of a transaction contains two fields. It has the value and the data, and transactions can have both the value and the data, or it can have only the value or only the data, or it might, let's say this is a field that is optional. When it's optional, it means that, let's say if it's optional and you don't have the value and the data, it can just stay like this field might be missing on the fields of a transaction. When, let's say, this field exists, it could have the data and the value, or it can have either of them. So all four combinations are valid. So either if it was taken as optional and nothing is there, it's still valid. If it has the two or either of the ones, it's still valid. So a transaction with only value is a payment. So value could be, let's say, the amount of Ether that someone was sending the recipient. So a payment transaction will have only the value, and then a transaction with only data is an invocation transaction. So normally, mostly invoking, I think you've heard invoking a smart contract. So let's say when someone was trying to invoke a specific function of a smart contract, a transaction will still occur, but now it won't be a payment, but an invocation. But it's still a transaction. And then transaction with both value and data is both a payment and invocation. So this, let's say for a case of a smart contract, let's say an NFT. So the common thing on an NFT project could be the mint. So when someone, let's say, tries to interact with the smart contract and they just click the mint, that will be invoking the contract. And then now maybe going ahead and confirming this, because let's assume to mint this, you'll have to connect your MetaMask wallet, and let's say going ahead and really minting it, you'll have to confirm the transaction, which you'll be making a payment. So a transaction with neither the value or the data. So for a case of a transaction with neither of them, it's probably just a waste of gas, but still possible. So here they're just trying to explain the possibilities of the transaction data. And there is that one for payment, the other one invocation, or if we have both data and value, that's payment and invocation happening at the same time. And if the field is missing, it could be just some gas was wasted, but a transaction still occurred. The next field of the transaction is digital signatures. And a digital signature is a mathematical scheme for presenting the authenticity of digital message or documents. So just trying to authenticate that maybe a simple digital signature could be just that, confirming a transaction. So with that, confirming a transaction, your private key will play some role on it, because let's assume you have connected your MetaMask wallet and then you confirm that transaction. So once you have confirmed it, it will have shown that you have signed that transaction. And this will show that now this transaction is signed and it's authentic. So a valid digital signature gives a reason, gives a recipient reason to believe that the message was created by a non-sender. Now that authentication. So let's say if you're trying to connect your MetaMask wallet for the first time, that let's say I try to open it right now, it will ask for the password. So even for someone to try and before they make that transaction, and maybe they're not checked on their MetaMask wallet, the first thing they'll have to do is enter the password of now the MetaMask wallet. And you know that already these MetaMask wallets, we already entered the seed phrase. Now everything is set up. I have the public key and the private key. So the only authentication process that I'll have to keep doing is entering the password. So when when someone is now here, they're just trying to say that to confirm that a digital signature is valid. So just for this digital signature, for it to be considered valid, it means that the sender, okay, is so this authentication is like login, but now we are using a wallet, and all someone can do to show that the wallet is theirs is maybe that entering the password because they have already set up. So for this transaction, it gives a reason for this transaction to be valid, that it's valid because it came from an authenticated sender, and also the sender cannot deny having messages. They can't say that they didn't facilitate this transaction or verify it. So the sender cannot deny having sent the message. Repudiation. Okay, they can't deny having sent the message or that transaction, and the message was not altered. It was not altered in transit. So just for every transaction, it has to have that digital signature, and the digital signature is for these three reasons: showing that it's from an authenticated user. Also, for this transaction, this user can't complain that they were not the ones sending that message or the transaction. And then also, there is no way that message can be altered during the processing of the transaction. And then, okay, we'd say that the digital signature is a mathematical scheme for now authenticating these digital messages or documents. So now seeing, let's say, what really makes up the mathematical scheme for these digital signatures. So we have two parts. One of them is an algorithm for creating a signature using a private key or a signing key from a message. So for this case, the message is the transaction. So there is an algorithm that creates the signature using the private key of now whoever is sending this transaction. So for me, let's say me as a user, it will be my private key for these MetaMask accounts that I'll be sending my transaction from. And then the second part is an algorithm that allows anyone to verify the signature by only using the message and the public key. Okay. So majorly this digital, let's say the mathematical scheme behind these digital signatures are just algorithms. Now verifying the signature, the process of maybe verifying that signature, because we are told in these two parts, the first one is creating the signature, then the other one is for verifying the signature. So now let's see verifying the signature. So to verify the signature, one must have the signature. So I think you remember yesterday I went and checked that. I can't remember the word in full. Just a moment. I think it's here. let me yeah. You remember when we were seeing the V and R, there was this ECDSA, which is the algorithm for creating the digital signatures. So at the moment here, we want to look at verifying a signature, these R and S. And now the thing that is behind all this is okay. I'm sorry, I lost my connection. I hope I was still here on verifying the signatures. So I was trying to talk about the elliptic curve digital signature algorithm. And the reason I'm checking this elliptic curve digital signature algorithm is yesterday we had said that this is the algorithm that is used to create the digital signatures for a transaction. And here, when we are talking about verifying the signatures, we are told that one must have the signature R and S, and then apart from the signature, there should be the serialized transaction and the public key that corresponds to the private key used to create the signature. Now, this public key could be the address of the sender, and then the private key, of course, it will be the private key still of that MetaMask account, or from which that address was from, which obviously the private key will correspond to the public key. And yeah, to make it valid, because there are key pairs. So these are the three things that are needed for the signature to be verified. So it's the signature, the serialized transaction, and the public key, which corresponds to the private key that signed that transaction. And then essentially, verification of a signature means that only the owner of the private key that generated this public key could have produced this signature on this transaction. So just maybe why there is this verification is, okay, sorry. So Maybe just the essence of this verification of the signature is just to see that this private key corresponds to the public key, and that will mean just that the sender was able to confirm or sign that transaction. So the signature verification algorithm checks the message or that transaction. So a hash of the transaction for this case. Okay, it will check that message, but as we are talking about transaction. So it will check the hash of this transaction, the signature, the signers or the senders public key, and the signature, the R and S values, and returns true if the signature is valid for this message and the public key. Okay, so there they were just explaining the verifying. So for verifying, they'll need the three things, which is the signature, the public key, and the serialized transaction, which now this serialized transaction is an hash of the transaction. And once it's confirmed that the private key that signed the transaction matches the public key, it will return true. So that's all about verifying the signature, and also that's all about the fields of a transaction. So that was the last slide. So in case anyone has a question or anything you want to be addressed, this is the time. Thank you. Is there any? Is there anything that you want to be addressed or a question in what I've been covering? That, yeah, can go ahead.
Good afternoon, Sharon.
Good evening.
Can you hear me?
Yeah, I can hear you.
Okay, good evening. Yeah, the other time when you were talking about the recipient, you were saying something about even if the transaction doesn't go through from the sender, if the sender should send a transaction and doesn't get to the recipient, it's still a transaction. I don't know. That one is really, it's not clear to me. Then you said the digital signature contains two parts, which is the algorithm for creating the signature using a private key. That's the signing key from the message. And that algorithm, is it the one that allows anyone that the message is being sent to view the message or to receive the message? I didn't get that part, please. Can you clarify that part? Thank you.
Okay. Yeah, I'm sorry. I'm talking, so I'm muted. I'm sorry. So I was explaining the first part, which was the recipient's address. And that time I was trying to explain that in case someone is sending to an address, and let's say you are sending someone you know and they have sent you their address. So, and you know the address is 20 bits. So let's assume you missed one digit and wrote a wrong digit, but still this address will still be 20 bits and it will still be a valid Ethereum address. So I was saying that as long as it's still 20 bits, it's still a valid address, whether let's say it doesn't have a matching private key, or maybe for a case of a contract, it doesn't have a corresponding contract, this address will still happen. Like whatever you are sending will still be deducted from your address. But now, since wherever you are sending to is not actually valid, like that address was wrong, that transaction will still be successful. But now that, let's say, the ether you are sending will be banned. Yeah, so that transaction will be successful. Then I'm not sure if the next part, if that first part is answered well. Can you hear me?
Yeah. Like the transaction goes through, even if if it does not get to the recipient, the transaction still goes through, but it turns to a bond ether, right?
Yeah. Okay.
Okay, I got
Can you
that. Then the
clarify?
second question.
Yes.
What
Clarify
I
this.
got from where you just the second question, right? I said
Yes.
the digital signature, you said it contains two parts. To confirm the authenticity of the message that you are sending, so that they will know that this is the actual person that sent it, it's coming from this actual sender. There's supposed to be a digital signature. And he said this digital signature is going to contain two parts. The first part is the algorithm for creating the signature using the private key from the message that is being sent, which is the transaction. Then the second part is the algorithm the algorithm that allows anyone to be able to view the message that is sent, or the algorithm allows that person to receive the transaction that is being sent. I don't get. Does it allow the person to view it, or it allows the person to receive it?
Yeah, I've gotten your question. So when we were talking about these digital signatures, so of course we said it's a mathematical scheme and it contains the two parts. And the first part is the algorithm for creating the signature. So this algorithm uses the private key that you use to sign your transaction. Yeah, so through, like, the algorithm will just use the private key and the transaction itself to generate or create a signature. And then the second part is an algorithm for verifying the signature. So this second part, or this algorithm, is now used here in verifying the signature. So you're seeing here, they're saying that it's an algorithm that allows anyone to verify the signature. And when we are talking about verifying a signature, you'll need the three things, which is the signature that was created by the first part, which is the algorithm for creating the signature. So once that signature is created, you'll need it as part of the things needed to verify the signature. So you'll need the signature, the transaction, So whenever you make a transaction, the transaction will have an hash. You remember the hashing. So transaction will have its own hash. So you'll need the signature, then the serialized or hashed transaction, and then the public key, which for us, the public key could be the address of the sender. So you'll need these three things. And then now you remember this algorithm will now, like with this algorithm, will compare the three things: the signature, the hash transaction, and the public key with the private key that signed this transaction. So the only thing we say that anyone can verify the transaction. So this anyone who is trying to verify this signature will just be checking if this public key corresponds to the private key that signed this transaction. I don't know if that makes sense.
Yes, thank you.
Okay, does anyone has a question? Any question, even for things we learned yesterday? Because I've finished presenting for what we had for this week. So I'm taking any questions or concerns, just anything general that you want clarification on. This is the time. Okay, so I believe, because let's say, unlike the preface, maybe you'll get the slides today, and then okay, I'll check the question. What else? So there'll still be a session, I think tomorrow. So it won't really be like this one, but just another session related to class, and a different mentor will come for that session. So there is a question here. So the question reads, is there a way to validate the address to ensure that it's truly an address, front-end wise, aside from the fact that it is 20-bit? Okay, I would say that since the way we, let's say, went through there, and they say that the recipient address, Ethereum doesn't have a way to validate whether this is actually a valid address. So for them, as long as it's 20 bits, they'll consider it valid. So for front end, it will depend with the creators of that front end. Like now, let's say the guys from MetaMask, they might have a way to, they might create their own way to help a user validate or check if that address is valid. So it will depend with, let's say, the UI or the user interface that you're using. If for them, they already created a means for you to validate. And of course, there was that warning that for you, before you just go ahead with that transaction, just try to confirm. So, and of course, as mostly they say that Web3 still has a challenge when it comes to user experience. So the blockchain might be good, but now much work has to be done on the user, let's say, user interface or user experience, so that these small, let's say, errors, like now having an invalid address and the ether ending up being banned, maybe the guys who are maybe creating these user interfaces, they can come up with ways to help users validate their addresses, and this could be one of the things that need improvement on the front ends. Any other question? I hope that was answered. Okay, thank you. So we still have, I don't know, I think is it 26 minutes? If anyone has a question, you can ask, or if there'll be none, you can ask even maybe about me or something, anything. If there won't be any, maybe we'll end early. Okay, that means there is no question, and I just hope that today, or maybe I took you better. Okay, we will end early. So I hope today's class was better than yesterday, or you got it better.
Yes,
And
it was.
everything. Okay, thank you.
Yes, it's better.
Yeah, it was better.
At least better than yesterday's one. The network and all. Even the class
Thank
was
you.
explanatory.
We'll get better with time.
Ma?
I'm just saying that it will get better with time also.
Yeah, sure. Thank you very much, ma.
Thank you. So maybe the last thing, you know that the channel is yours, the Web3 channel. So in case of anything, you can always be posting on the channel, or in case of any concerns, so that we can get back to you.
Okay, no problem.
Okay,
Thank you.
All right.
okay, thank you.
Thank you very much, ma.
Thank you.